All right, thanks a lot, James. All right, so this slide shows an example of cluster analysis output from the 2019 Traffic Analysis Toolbox Volume 3 method. So the results here show that each cluster exhibits substantially different traffic network performance. So ideally, the TISMO strategy should allow for reliable travel times throughout the year under all operating conditions. So when you consider the data shown in this table, you can start to envision how misleading a microsimulation project might be if it only focused on one set of so-called typical conditions, or even trying to design for the 85th percentile conditions. Instead, only by explicitly developing and calibrating each of the models shown here would it be possible to assess the annual performance of different alternatives under consideration. And when it comes to reporting the annual benefits of a certain alternative, TAT Volume 3 suggests including all clusters in that calculation, including what might appear on the surface to be the low priority clusters or minimally congested clusters or low probability clusters. So for a robust analysis, it's safest just to include and consider all the clusters. So again, the project pertained to case studies intended to show the benefits of the TAT Volume 3, the 2019 method. And so the case study project included deliverables such as a case study selection memo to try to identify the most pertinent 3 real-world case studies from across the country. Secondly, a case studies report that will hopefully be published within the next several months. Thirdly, we have today's national webinar is one of the deliverables of the case studies project. And fourthly, there's a series of 3 conference presentations as part of the deliverables as well. And the final deliverable is a white paper on future recommendations related to improving the information available for TAT Volume 3 and announcing different opportunities for using it in various venues and mechanisms, and how to potentially improve the methodology in the long-term future. Thank you. All right. So this slide here shows the 7-step microsimulation analysis project, microsimulation analysis process that was originally published in 2004 before being updated in 2019. And so although the slide implies that the biggest changes in the 2019 method pertain to model development, calibration, and alternatives analysis, the step 2 data collection and analysis step also features significant changes because that's where cluster analysis now occurs. And so now, Matt, I think we can advance to slide number 8. All right, excellent. So the upcoming case studies report will contain the 7 chapters listed on this slide. So notably, chapters 3 through 5 each focus on a singular case study, which we'll be hearing about in today's webinar, whereas chapter 6 documents the findings of some extra research experiments that didn't exist in the original scope of work. So next slide, please. So the research team originally considered a pool of more than a dozen candidate microsimulation case studies from real-world locations. The goal was to select 3 final case studies whose published results could complement each other and provide maximum insights. So to achieve this, the final case studies would need to feature a healthy variety of alternatives to analyze, different operating conditions, different microsimulation tools, and so on. And there were also prerequisites for high-quality case studies. And those prerequisites included access to rich data sources, support of local agencies, and pre-existing microsimulation models. Next slide, please. So to discuss the details of the first case study from Florida, I'm going to hand off to Dr. Mohammed Hadi. Thank you.
Thank you, David. As David said, this project selected 3 case studies, and Florida is one of the 3. The corridor or the network that we selected for the case study is I'm trying to start my video. Yeah. Okay, so the network is in South Florida, in Fort Lauderdale, Palm Beach area, and it includes an interchange that between 2 freeways, a system interchange between the Sawgrass Expressway and the Florida Turnpike. It has around 6 miles on both facilities, And the main issue with that interchange is in both the morning peak and the afternoon peak, there's a weave area for the northbound on and off ramp from the Sawgrass and Expressway and to the Sawgrass Expressway from the Florida Turnpike. That weave area back up in different days differently. And if we are going to do the analysis, assuming that this backup happened in the whole year, and activate TISMO strategies or geometric design strategies, as David said, we're going to be biasing the results because several of the in the off season, which is in Florida in the summer, and other days we have less congestion. So we got data from tools, toll readers, and data station and fixed sensors. And we then analyze the system using a commercially available software. Next slide. Again, we look at through the whole year, we want to look at the congestion variation and the benefit from applying alternatives using the methodology, TAT Volume 3 methodology. The key performance measures are travel times on the main line and the on-ramp, which both of them back up due to the weave area, and the bottleneck throughput at both the ramp and the freeway main line. We use 3 hours afternoon peak period. Obviously, if it was a real world project, we would have done that also for the other peak, especially the morning peak. And that is because the similar backup happened in the morning peak. The analytical approach, we analyze both weekdays and weekend data across the 2 critical routes, the ramp and the main line. We use heat maps, fundamental. Obviously, we simulate the whole network, the 6 miles on the Sawgrass and the 6 miles on the Turnpike, but the focus in terms of the analysis, obviously, and reporting the results was for the ramp and the main line. We use visualization tools, which were very helpful for us when we look at the data. We use heat maps, fundamental diagrams, cumulative density functions, and that in addition to the fundamental diagram, which the speed of flow relationship, and analysis of traffic patterns and travel time reliability gave us a good idea even before we start the clustering about what is going on with the network and what are the situation and scenarios. Next slide. So the data we have is volume and speed from microwave traffic detectors and a detection station, and also volume from toll tags. And fortunately, we have the few locations where the toll tag readers are in the same location as the count station. So we were able to confirm that the count station are able to provide similar results to confirm the accuracy of the 2 sources, confirming each other that way. Travel time, we got it based on the RETIS data archive, which is mainly from a third-party vendor and of travel time. And then we got rain data from the National Weather Service, and we got incident data from the FDOT incident and crash database. Next slide. So we identify when we run the simulation or the cluster analysis, we found out there are 4 clusters. 2 clusters were light or very low congestion. One of them represents the weekend, and one of them represents the mainly represent the weekend, it seems, and the other one represent weekdays with low traffic and that's low travel time, low traffic volume, and that's low travel time. The cluster 2 and 4, they differ in mainly in the period of congestion. So cluster 2 has congestion for 3 hours of the peak. It starts like 3:30 and continue until 6:30 or so on. While the other cluster has congestion for 30 minutes or 45 minutes around the 5 p.m. Peak period. So obviously these different clusters have different implications, and the alternatives that we're going to evaluate, especially if they are TISMO alternatives, will have different benefits, different strategies, and so on. Next slide. We found out that the resulting clusters did not cluster the incident and weather events in a separate cluster. And we think that a lot of this because there are a lot of the incidents in that location are shoulder incidents, not many severe incidents. Also in Florida, most rain events happen in the summer that correspond to the off season. So which has less traffic. Again, the clustering, because of the issue with the data, we have only 294 days of the 365 that we isolated out the 365 days. And you can see the numbers. So the two congested cluster, the one with 3 hours of congestion is cluster number 2 with 40 days. And the cluster with a shorter period around the 5 p.m., around 45 to 1 hour, is the one is cluster 4 with 104 days. Next slide. So if you look at this table, it shows you the travel time, and you could see that cluster 4 again, both the average and the maximum are high. Cluster 2, I mean, both the average and maximum of the travel time are high, while cluster 4, you have the average is low, relatively low, and the maximum is relatively high because of the congestion in the 30 minutes to 1 hour during the day. The other two clusters, both the average and the maximum, are similar, and they present the free flow condition for cluster 1 and 3. Next slide. So an important step in the volume 3, which is different from the current methodologies, in addition to clustering, which is an important concept in the methodology, another difference than state guidance and volume 4 methodology is the calibration based on the representative day and based on new criteria. So you could see here that the representative day should fall between this is basically representative day and showing the 1 sigma, 1 standard deviation, and the 2 sigma. Next slide. Yeah. So no, the previous. Yes, this one. So basically, these 4 criteria are different from volume 4, which some are familiar with in terms of percentage error and so on. This one is ensure that the simulation results, which are the purple dots, fall within 75, the 1 sigma and 2 sigma, with a certain amount from the representative day. So 95% should be within the 2 sigma and 67% should be within the 1 sigma from the representative day. There are two other criteria that has volume 3 present equation for. One of them ensure that the error is lower than for the representative day than all the days, and also the other one, the fourth one, ensure that we are not consistently underestimating or consistently overestimating the performance on all periods in the peak of compared to the representative day. Next slide. When we look at the model that was already calibrated based on the state agency criteria, we found out that we needed to refine it and fine-tune it. So we changed the car following and lane changing model, and we used the FDOT guidance of the ranges of those Weizmann 99 car following and the lane changing model. And we study the congested clusters 2 and 4. Volume 3 recommend analyzing all the clusters, and we recommend that to be done. But for this demonstration, we only analyze cluster 2 and 4, and we justify that by the other being light. But for real-world situation, that it is a decision that has to be made carefully, and the preference is to make the analysis for all clusters. Next slide. So you can see that also the volume 3 presented a new methodology to calculate the number of runs. We always use, obviously, the t-distribution, if you are familiar with that equation, to calculate the number. We're still using the student distribution equation for the analysis, but we have a variation of it in terms of calculating the tolerance and so on. But in any event, the recommendation is to calculate the required number of runs based for each scenario and for each route, and then select the maximum number of runs that are needed. In this case, 13 runs were needed for one of the scenario for one of the routes, and that's what we run the model for. Next slide. Oh, before we do that, I think we assessed two alternatives. One of them is to deploy ramp metering, and one of them is to move the off-ramp downstream from the weave area. Move the on-ramp downstream from the weave area to eliminate the weave area. And obviously this solution is expensive. It's very high cost. There is an estimate for that cost millions of dollars, and then the other ramp metering is low cost alternative that can be done much more easier. So next slide. Based on this, we did the evaluation both based on percentage change, but also using hypothesis testing as recommended in volume 3, statistical hypothesis testing, using also the t-distribution. So if you look at the results, we see that alternative with relocating the ramp, obviously it gives very high improvement for the ramp, minus 9%, and for the main line, minus 72% reduction in travel time, while for the ramp metering, it increased obviously this was not totally optimized ramp metering. We use the Alinea algorithm that is built in the tool, and we fine-tune it a little bit. So in this case, we got 27% reduction increase in the ramp and travel time, and 9% decrease in the and the main line with the ramp metering, but there are opportunities obviously to modify the geometry in combination with the ramp metering and do other techniques to optimize the ramp metering strategies. And then we could use this to do the benefit cost analysis, because then you know that we have 40 days with cluster 4 and 104 days with cluster 40 days with cluster 2 and 104 days with cluster 4. So you could do benefit cost analysis this way. So I think this is my last slide. Is that right? Yes, and pass it to Paul. Thank you.